You cannot offer me any amount of money that would make me go into one of those loop-de-loop roller coasters. From the outside, they look fairly safe, and technically, the mechanics sit on their side. Let me explain. What you have here is you have the centrifugal force, which acts away from the circle, but it is also the centripetal force acting towards the circle, mv squared over r. Long story short, the faster you move, the more force is pressed against the rails. This is the thing that keeps you stuck to the loop. So at the top of the journey, the forces acting on it are going to be mv squared over r pushing outwards and mg moving downwards, leaving one more force, the reaction. And if the reaction is zero, that is the moment at which you're essentially falling. Hopefully that never happens. Think of it like the water in this bottle. If I spin it hard enough, essentially the water is going to constantly stay on top of the bottle and never fall. But as soon as I slow it down, the water will fall down. Yes, I know there's a cap on it, but I'm not about to make a mess in my apartment. It is what it is. So, the main idea behind this is that at the top of the journey, you're going to make all the forces an equilibrium equation, and you're going to equate r being equal to 0. This gives you then mv squared over r being equal to mg. So technically, the minimum velocity that you would need to stay stuck at the top of the loop would be just square root of rg. To put the numbers into perspective, if I had the radius for this loop of 10 meters, which is not unheard of, you would need to travel at 10 meters per second in order to be able to stay on the track. For the sake of a comparison and analogy, 10 meters per second is the equivalent of Usain Bolt's speed. You would expect a train to move faster. But if anything in this world, this is one ride that I'm unfortunately going to have to pass on. I am a man of science, but I'm also a man of faith, and when that instinct tells me to run away, I generally do.